Mm. Oh, shit. Sorry. Hi, I'm live, aren't I? Hello. Hi, friends. This is approximately 6 hours late. Why is it 6 hours late, you ask? Excellent question. I see nobody's here because I'm 6 hours late. That's okay. I'm gonna chat and just talk for a little while. Why am I 6 hours late, you ask? I'm gonna put this in the chat because I have a toddler, and that's what happened. And I forgot to change the time on here. Um, Hello to the one person watching. Hooray. Okay. But we are going to do Journal Club and we're going to do it live and it's going to be so great. And I am going to remember to plug my computer in to the hard internet. Hard internet. What's the word? Hardwire it in. There we go. Hi. Yes. Okay. Excellent. I see one person here. Lovely. I'm going to pull up the article we're going to be looking at while we all just kind of have a chat. Okay. Oh my goodness, everyone. Things from my end. Lots of stuff is happening. I've turned in my dissertation, which is exciting. Um, oh, I see Kip Davis is live right now. I bet my viewership overlaps with his a lot. That's just fine. Okay. Do 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 do. Okay, that's okay. I want to go to YouTube Studio and pull out the article. So my dissertation is written. It is with my committee. That is very exciting. Um, and um, my defense is on Tuesday, which is going to be great. I've got my slides made. I've been practicing my presentation. I think it's going to go super well. Um, and yeah, that's what I want to look at. Okay. We're going to do a live stream here Thursday night where I have some whiskey and enjoy and deeply enjoy my oh no, that's not the one I wanted to look at. And try for me to redo my defense, but with whiskey. So that's gonna be super fun. I've got like a bunch of the science team potentially coming to that. Invite is out. So that's gonna be hopefully like an open kind of fun time. And I'm thinking maybe if that goes well, maybe making it like a series. Um, we're going to look at more of the heat problem today. That's where I want to go to. I got really mad at that Milankovitch cycles paper a couple weeks ago. But today we're going to look at heat problem Genesis flood model and just keep reading that paper together. Yeah, sure. We'll save it. And then we're going to pop back over here. Okay. And now I'm going to open it up. And we'll get to reading. We're going to get to reading. I'm so sorry to everybody who came by earlier today when this was actually scheduled. That was, yeah, listen. Sorry, baby girl is perfect and good. And having a toddler is kind of hard. But that's all right, you know? That's okay. I'll just close that maybe. No? Okay. Well, whatever. Okay. All right. So let me share my screen and we'll look at the paper and we'll try to, it's this heat problem paper is what we're going to get back to. So I'll keep an eye on chat. Let me know if you guys have questions or want me to look something up. And, oh no, window. That's what we want. Share that. Excellent. Um, there we go. Perfect. Okay. So, oh, who is the dog in there? That's my sweet boy Chester. In my picture in the thumbnail. He's a very good nervous little healer. Okay. So, where we left off with this paper, let's see. Was it ocean temperatures? I think we can talk. Yeah, okay. I think we can go through the ocean temperatures. Okay. Excellent. We'll start here. We'll start here. Okay. In ocean temperatures and like paleoclimate ocean temperature stuff. Okay. Because this is yeah. Okay. So we've talked about the Milankovitch cycles. The purpose of this paper is it's not a science paper. It's just not written like one. And so it hurts my brain. It causes me pain to say that this is a paper. This like article, let's just call it an article. I'll feel better about it. Has been explaining what the interior structure of the Earth looks like in terms of temperature, how we know that. Okay. And now we're going to talk about how we know ocean temperatures. And what this article is trying to do is establish, like in the physical world, boundaries, like the boundary conditions for how much heat the Earth could have possibly like transported into the mantle, right? So assuming the flood happened, and they use, I think, catastrophic plate tectonics. Yeah. Um, is their assumption for that? Um, they want to know, like, okay, how much heat was produced? What evidence do we have for how much heat could have possibly gone into the mantle, et cetera, so forth. So let's take a look. Okay. Ocean temperatures. Considerable geological evidence is available relating to the Earth's past ocean temperatures and ice cover. That's true. Um, okay. The temperature data comes from marine deposits from the whole span of the geologic record, notably from the Phanerozoic fossil shells. Yes, so he's going to keep explaining that, but I'll squawk if this is wrong. The record is particularly rich for ocean floor sediments, thanks to extensive ocean floor drilling programs carried out over the last 50 years via the International Ocean Discovery Program, exploring the Earth under the sea. I'm not familiar with that specific one, but that sounds right. And its earlier incarnations. That doesn't sound like a creationist thing, right? That sounds like a real science thing. The resulting data is publicly accessible via the Pangea online database. Geologically, which is great. You love to see, I love how much of geoscience and meteorology in particular is like all of the data is just open and available for anybody. You'll love some open source science. Geologically, most ocean floors are identified as Jurassic, Cretaceous, or Cenozoic, i.e., not exceeding 200 million years. And I refuse to say that word in normal science terms, although the Ionian Sea and the Eastern Mediterranean are dated from about 270 to 230 million years. Okay, yes, so this is because the Earth recycles its crust. And so ocean floors are like, so continental crust is harder to make and takes longer to destroy than ocean crust. So ocean crust does recycle itself about every 200 million years. And that, like, you get about that number if you take the rate of seafloor spreading at like the center of like the Atlantic Ocean, say, and you calculate, okay, well then how long does it take for a piece of crust we just made, assuming the spreading rate is constant, how long would it take for this piece of crust to get all the way to where this ocean plate is diving under a continental plate? And the answer right now is about 200 million years. Yeah. So that is, if you saw my face, that was like, wait, is it 200? Yes, that is the number. I just second guessed myself for a second. Um, So that order of magnitude, about 200 million years, is about the oldest seafloor that we've got. The youngest was made right this second. Um, and then, as you might imagine, it's like in the center is the youngest, and then towards the edges is the oldest. And that's our ocean crust recycling program. Only you can prevent forest fires. Okay. Um, Eastern Mediterranean and the Ionian Seas, if those pieces of crust are like more isolated, are not like actively subducting, that's how those could be a little bit older, et cetera, so forth. Okay. But in the CPT, so that's Catastrophic Plate Tectonics model of Austin et al. 1994, I'll have to read that at some point, in which the post-flood boundary is tentatively located at the KPG interface. Oof, that KPG interface, by the way, team, that is, I'm going to turn off my Wi-Fi. Okay, there we go. The KPG boundary is uh yeah, Cretaceous, Paleogene. That's also like the global iridium layer from the asteroid impact. Um, So in this catastrophic plate tectonics model, they're going to put that as the where the flood starts. These stratigraphic assignments correspond to mid-flood to post-flood times. Okay, so they're saying all of this seafloor that formed over 200 million years is laid down, not even over the whole flood time period. Cool. How are you going to make that much crust that fast, my dude? How? In other flood models, the correspondence of ocean floor development with flood chronology varies according to where the flood post flood boundary is placed. See Section 3 for further discussion of alternate flood models. So excited to do that. The most widely used temperature and ice cover indicators are the oxygen isotope ratios. That's true. The ratio of oxygen 18 to oxygen 16 in marine, fossil shells, and in ice. Hence the term oxygen isotope paleothermometry. Listen, science, we do love our big old words. This has been complemented over the last 20 to 30 years by other temperature indicators, including fossil shell magnesium to calcium ratios, coral, strontium to calcium ratios, biomolecular indicators, and clumped isotopes, which are all reviewed in the next paper, part 2 in the series. You love to see it. Okay. But this is the Okay, so oxygen has 3 table isotopes, oxygen 16, 17, and 18. That is true. For y'all to remember that oxygen 16 has 8 protons and 8 neutrons. Oxygen 17 would have 8 protons but 9 neutrons. And oxygen 18 has 8 protons and 10 neutrons. With the respective abundances on Earth being oxygen 16 is 99.757%. I don't know if that's exactly right, but that sounds right. And it's on any periodic table. So that would be a silly thing to lie about. 0.038% and 0.205%. The bracket, yeah, blah, 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 blah. The parentheses indicate uncertainty. Okay. Then the oxygen 18 to 16 ratio. So what that means, right, is that if I went outside and I like grabbed a bunch of air, I put air into a balloon from outside and I measured how many oxygen 18 atoms were in there and how many oxygen 16 atoms were in there. There should be 99.757 oxygen 16 and 0.205% oxygen 18. But what happens is that in certain samples, that ratio will be different. And hopefully this kind of explains that. So we'll keep reading here. Um, so this delta 18 fraction is the ratio in the sample versus the ratio of the standard being these numbers here, and then -1 times 1,000 to make it bigger. And because they're quoted as parts per thousand or per mil. Okay. Cool. Um, love it. Okay, so this is what that oxygen isotope paleothermometry is founded on: the temperature dependence of oxygen isotope fractionation between authigenic minerals and ambient waters. Okay, so yeah, this is a thermodynamic effect favoring a slightly higher proportion of heavier isotope in the mineral than in the water, but that weakens with increasing temperature. So what that says is that um, if ice freezes now, um, uh, when ice freezes, it like so if I look at ice versus water, the amount of oxygen in that ice is going to have more oxygen 18. That's like what's going to freeze first than the oxygen 16, right? So I could take like ice and water. The ice has a little bit more. So it's like the colder it is, the more oxygen 18 is going to be incorporated into the ice relative to the amount of oxygen 16. So this ratio goes up with colder temperatures. Um, so under equilibrium conditions, that ratio of precipitating carbonate and phosphate minerals. Oh, excuse me, I said that for ice, but I meant it for like calcium carbonate, what you make shells out of. Yeah. Yeah. So when you're making a mineral using oxygen that is in water, such as calcium carbonate, that makes the shells of critters, which is why critter shells are so good for telling us about past temperatures. They're such a good paleoclimate tool. Cool, 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 cool. So the colder it is, the bigger this ratio will be. Colder it is, bigger that ratio will be in our like calcium carbonate shells. Okay. We're not going to read all of the details of that, talking about like, is it blah, 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 blah. Okay. Oxygen isotope paleothermometry of Paleozoic and Mesozoic marine fossils is largely based on the shells of brachiopods and bivalve mollusks. Ooh, uh, belemnite guards, the bullet-shaped ends of belemnite fossils, and con- conodonts. Sure. Um, so it's all this is saying is that like what types of shells you use depends on the era, which we all know means um that good. Okay. Uh like you can only test what existed. Right? Um in the Cenozoic it's different. Um okay, cool. Calcium carbonate fossils are the most important for scientific study. All of the organisms mentioned in this paragraph above produce calcium carbonate fossils, with the exception of conodonts, which are made of calcium phosphate, but that phosphate is still going to have oxygen in it. The calcium carbonate, is only important because it has a lot of oxygen in it. Okay. Um, okay. Oxygen isotope fractionation also occurs when water evaporates. So H2O18, so water molecules that have that heavier isotope, which are heavier than the more abundant H2O16, preferably remain in the liquid phase. So it's H water with oxygen 16 in it is slightly like lighter than water with oxygen 18 in it. And so oxygen 16 is going to be slightly easier to evaporate. Um, Meaning will preferentially leave oxygen 18 in the liquid state. The resulting water vapor is correspondingly depleted from oxygen 18, water containing oxygen 18. Consequently, rain or snow resulting from condensation of atmospheric water vapor has a lower oxygen 18 value than the original seawater. So, this is getting at when we're looking at ice cores, like freshwater ice cores, not seawater. Freshwater ice cores um, should have like extra oxygen, excuse me, too little oxygen 18 relative to normal. Um, Condensation also causes fractionation, such that the water vapor remaining in the atmosphere becomes further depleted in oxygen 18. Most heat and mass transfer from the oceans to the atmosphere occurs at low latitudes. That is true. You don't. So this is saying is that you don't get a lot of. So you get a ton of ocean water evaporating up into the atmosphere around the equator. Much less of that happens at the pole, right? Um, so okay, followed by transfer in the opposite direction at higher latitudes. That's true. This is think of this as a big old cycle. This is like Hadley circulation is what it's describing. We actually have 3 cells, and I'll talk about that briefly. So at the equator, air goes up. We're evaporating water up into the atmosphere. That water is going to travel poleward, so north in the northern hemisphere, south in the southern hemisphere, and then it's going to sort of get too heavy and cause and sink down, right? And that on Earth is at about 30 degrees. That's a function of planet size and how fast it spins. So the Earth has 3 cells. Jupiter has lots of cells. If you look at a picture of Jupiter, you can see all those little bands. Each of those is a cell where closer to the equator, it's rising and then sinking closer to the pole. So we have the sinking motion at about 30 degrees latitude, which actually that's like the latitude of the Sahara Desert and like deserts in Arizona, ish, right? So we have these global desert regions where you have that descending air. And then, so air descends there around 30 degrees. So we also have air that ascends around 60 degrees. This is called the Ferrel cell. And it goes poleward, so it sinks down at the poles. So Antarctica, for example, is like a desert, right? You don't get a lot of precipitation there. Hope that makes sense. So yeah, a lot where you're evaporating water is from lower latitudes and you transport that into the higher latitudes. I just threw a hair tie somewhere around in my office. Oh, hello, 5 people watching. If you guys have questions, I can see the comments, so let me know. Yeah, whatever have you. Thank you for being here. Okay. Okay. So okay. Hence, atmospheric water vapor becomes progressively depleted in oxygen 18 as it moves poleward, such that oxygen 18 value in precipitation decreases as the air cools. The further poleward you go, the colder it gets. Further orogenic, high altitude precipitation becomes progressively depleted in oxygen 18 as the air rises and cools. These processes are known as Rayleigh distillation. That is true. Okay. Is this really distillation? No, but all of that is just trying to say that oxygen 18 is depleted in ice. Um, and the greater the global volume of ice, the greater. Oh, hi, epsilon is greater than. Yeah, it's been half a minute. I've been taking a very long break from, unfortunately, a very long break from YouTube because of finishing my dissertation and having a baby. So the baby is now a toddler and my dissertation is turned in. My defense is Tuesday. Okay. So the greater the volume of ice, the greater the inventory of oxygen 18 residing in the oceans and atmosphere. Yes. Okay. So the more depleted an ice core is in oxygen 18, the smaller that ratio, the more ice is covering the planet. That's what that's trying to say. Katiana, thank you so much. I think it's going to go well. I've been practicing. I've suckered my sister into listening to me practice tomorrow. And like I said, I will share all of that with you good folks Thursday night with some libations. So that will be super fun. Okay. Anyway, so all of this to say, okay. Oof. This oxygen, he's going to talk about that paper and it's going to make me angry. The oxygen 18 value in seawater and hence in marine fossils becomes a proxy tool for high ice volume. High values of oxygen 18 in the oceans imply large ice volumes. This effect was first established by Shackleton in 1967 and further developed in this paper. This is linking the Milankovitch cycles. Yeah, so we know we have periodic ice ages. There's evidence of that in our, like in the ice cores that we drill and in paleoclimate and marine fossil stuff. And we know that they're periodic, right? So we have periodic ice ages. And that periodicity ties to the Milankovitch cycles. And the last one of these journal clubs, I talked all about the Milankovitch cycles and how they cause stuff. So I won't, as much as I want to yell at someone for being wrong on the internet, I will resist. Okay. Because of the not just apparent, of the real explanatory success of the astronomical theory, it now serves as a ruling paradigm in the climate research and is often used to calibrate climate data chronologically, notable isotope records in the deep sea cores. However, this theory suffers from serious methodological flaws. It does not. That's not real. Okay. But oh no. Okay. In summary, assuming the normal chronology, the most critical problems are orbitally induced changes in solar radiation are very weak, especially the 100,000 year eccentricity cycle, which appears to have the astronomical forcing paradigm to have dominated climate variations over the last 400,000 years. Um, it's not that hard. It's like a sophomore, junior level undergraduate math problem to calculate like the average temperature of the Earth given like certain atmospheric conditions and what the incoming solar radiation is. And so saying that like, hey, but the change in solar radiance is very small. My guy, do you think nobody checked that? Like the math is really easy, you know? Um, I mm, I could sit here and do it if I have a textbook. Oh, I don't think I have that textbook here. I need to look up some of the equations because I don't carry those around in my head. Um, yeah, but it's not that complicated. And again, like do you think like the change in the tilt of Earth's axis that causes the difference between summer and winter, you know what I mean? Like it doesn't take a big change to cause a big difference in what we experience, right? Anyhow, ice age cycles are in phase between the northern and southern hemispheres. Um, Whereas the astronomical theory predicts the opposite. When the northern hemisphere cools, the southern hemisphere should warm up, and vice versa. Okay, like to a degree, um, but there's like energy exchange between those two hemispheres, right? So like um obviously when it's summer in the northern hemisphere, it's winter in the southern, right? But if what we're talking about is like changing the average distance the earth is from the sun, that's going to affect both hemispheres roughly the same. So like these ice age cycles, it would be an like it sounds like what he's proposing here is that um is that like if the northern hemisphere is in an ice age, then the southern hemisphere should be like a balmy 83, right? Which doesn't make any sense because the northern and southern hemispheres talk to each other, right? If that was the case, if it right, then um especially over long periods of time, um Star Song, yeah, Baby Girl is absolutely perfect. Um, and oh my goodness, toddlers are exhausting, and they need a lot, and I can't make plans anymore. um, and that's okay, but that's just luckily a lot of my friends are really flexible, and I appreciate your guys' flexibility. Oh, thank you so much, Red Cedar. I think it's gonna go well. I think it's gonna go well, and I'm excited to celebrate with you all after the fact. Baby girl is coming to my defense. She has a special dress for just such an occasion. Okay. That's right. But this idea that like one hemisphere should be in an ice age while the other is like really hot, like that type of temperature imbalance that's unsustainable. That's not the atmosphere would work to correct that. Right. Now, if we could like magically set it, it might take it like decades, right? It might take decades for ocean and atmosphere circulation to adjust it, but it would adjust if we're talking about like geologic timescales. Okay, and then causality. The warming, which terminates a glacial interval, sometimes precedes by several thousand years the change in solar radiation, supposedly causing it. I'm not sure that is actually true. I don't think it is. I think we looked at that last time. I can't like I don't have a graph to look at, so I don't know exactly where this claim is coming from, but that doesn't sound right. Um, the assumed age of the 700,000 years for the Brum's Mat oh my gosh, magnetic reversal boundary is used in constructing age models for the analysis, has since been revised significantly upwards to 780,000 years. Um, and their climate reconstruction on data from Plankton rather than so basically okay, so we have better data now. Um, uh, okay. So we have better data now. So what he's complaining about is that with less data, they got the gist of it, and now we have better data, and it's not exactly the same, right? So we have better data now, and the gist is still right, but the details have changed, right? And that's what he's complaining about here. And then in that crazy Milankovitch cycle paper we looked at last time of a reinforcement syndrome is what he said. Um, and oh my gosh, he concludes that the data sets have evolved over time, thus calling into question their supposedly objective nature. This is an argument that comes up in with climate change deniers a lot, which is, hey, like 30 years ago, we had less data and we predicted climate change. And then when we got more data, it supported those conclusions. In fact, it's worse than we thought it was. Therefore, they must be like manipulating the data to support their conclusions. Like, no, 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 no. Or we were right with less data and more data supports it, right? The more data is like, whatchamacallit, the more data is, um, uh, it's like the prediction, right? We made a prediction and then we got more data and it supported the prediction. That's good science, not making data fit your answer, right? If the data gave us a different answer, we would have changed our answer, right? Okay. When significant ice sheets exist on Earth, other climate indicators are needed. Yeah, more data, more better. Dave, absolutely. Um, When significant ice sheets exist on Earth, other climate indicators are needed to quantify separately the contributions of temperature and ice volume to oxygen 18 values. Sure. Notably, paleontological and geologic evidence of lower sea levels and the existence of and extent of ice sheets. That sounds reasonable to me. Um, in a flood scenario, oh no, we're going to get out of reason here for a minute. Rapid changes in ocean conditions are expected, which may invalidate some conclusions based on the usual normal, I refuse to say that word tonight, assumption of temporal near equilibrium for oceanic oxygen 18 levels. Detailed consideration of this issue is beyond the scope of this article. I wish you would spend more time on that, my guy, because that's like in a world where there was a flood, right? Um, in a world where there was a flood, that would be really important, right? Like that's what this whole paper should be about. This one little paragraph that's beyond the scope, apparently. So, um, it's true that, like, when you're thinking about reconstructing a paleoclimate data set, right? I want to know what the temperature was at this location for the last, um, 100,000 years. When you're talking about those long time spans, it's not a bad assumption to say that the ocean is in close enough temperature equilibrium so that there's not big differences in the oxygen 18 ratios between like this location and a location, say, 100 miles away, right? Um, when we're thinking about like when we don't need to know like what is the temperature at my house last Tuesday, right? When we're talking about what is the sort of average temperature of the United States for a 50-year period, right? Then you don't need that degree of precision, right? So paleoclimate data is talking about broad strokes, not what's the temperature like at this exact one point at this exact moment in time, but can this give us an average sense, right? Again, so it's the average temperature of the US, not the temperature at my house, right? That's what paleoclimate does. It's looking at these big scales. And so when you're considering those big scales, assuming that oxygen isotopes, like there's not going to be a big difference between one point in the ocean and another point in the ocean, right? They're all going to give you a picture of that big average. That's a good assumption. But if you had temperatures changing rapidly because of a flood, right? So inputting all of this different energy, it's moving around. That's a really, really dynamic environment. And if what you're saying is that, well, okay, these layers that took right hundreds of millions of years to lay down, no, actually that happened in a single day, right? Then and so the oxygen isotopes you're measuring there is just for that day, right? Well, then assumptions about like oxygen isotopes being in kind of being in like well mixed, being heterogeneous, right? Then that is a bad assumption because it's on a very short time scale. But for real science, that's a good assumption. And so, like, that's the first point he's brought up. If it was a flood, then this assumption is bad. Like, that's the first point that he brought up that I'm like, yeah, say more about that. Dig into that. Figure that out. Do that science. Right? And he's like, no, 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 no. That's beyond the scope. So I was like, come on, man. That's the first thing you said that's like, ugh, worth digging into, right? Listen, I enjoy like thought experiments, right? That's like one of my favorite ways to learn and to teach is thinking about so like when I try to like explain like how planet temperatures work. I like to start with like, okay, pretend that the earth is has no water on it, right? Desert planet, and it doesn't rotate and it doesn't have a tilt. It's perfectly up and down. Then what would our weather look like, right? And so you start from like that base idea and then like change it a little bit. Okay, now what happens when we start spinning? What if we doubled how fast the earth spins? Right? If you guys have been here, I like bothered to figure out what the weather, like the climate of Barovia would be, right? I did the same thing for like what would the gravity of Matt Mercer's Exandria be, right? I love like science fiction thought experiments, which is what this feels like to me, right? This like, but what if catastrophic plate tectonics? That feels like what would the climate of the Shire be? Right? That feels like a fun thought experiment. In a way that you can like learn stuff. Um so that's why I'm like, that's the fun that would be fun. Not a drop of rain on Arrakis. Yeah, my husband, uh, took me on, like, a after I turned in my defense on my dissertation, he took me, like, on a surprise movie date to see Dune 2, and it was really good, and I liked it a lot. Anyway, um, okay. Okay, all right, let's get back to reading this. So yeah, the one fun thing he brings up, and it's beyond the scope of this article. This is a six-part article, but no, this is beyond the scope. Cool. As anticipated by URI 1951, several factors complicate the use of fossil oxygen 18 as a proxy for seawater temperatures. Yeah, yeah, it's not easy to make um it's sorry, I'm such a distracted panda. It's not easy to make a paleoclimate thing, and there's going to be issues with it. But like, what's a better way to figure out what the temperature was 2 million years ago? Ecological influences, spatial variability versus temporal trends, preservation of the record. Yeah, here are the major sources of uncertainty and complexity will be considered under the heading of preservation of the original fossil, vital or biological effects, environmental effects, notably seawater, oxygen 18 levels. There is necessarily some interaction between environmental and vital influences because marine organisms usually respond in some way to changes in their environment. Cool. Okay. The issue is whether oxygen isotope ratios in the fossil shell material are maintained intact or modified by the higher temperatures and pressures of burial during diagenesis or by subsequent chemical reactions. Okay, so once a shell is made, it has a certain amount of oxygen 18, a certain amount of oxygen 16. Can you change those isotope levels via temperature and pressure? I actually don't know the answer to that. You would have to, I guess it could, like, that's like a geology and solid state chemistry thing. Um, it seems like it would be hard. These are not radioactive, right? These are both radioactively stable isotopes. So something would have to like come in and make the oxygen move out. Um, which I'm not sure I know enough geology to like understand what that process would be. Um, okay. So Ord, by the way, we don't like him. He's the guy that thinks Milankovitch cycles is bad. Star Song, absolutely, yeah. The Earth's rotation is slowing down, and the movement is moving further away from Earth. So the Earth's orbit right now, the way we spin and all of that, that is not like energetically the most stable state we could be in. It is much more common for planets and orbiting things to be tidally locked with the thing they're orbiting. So eventually, yeah, the Earth will be tidally locked with the moon. Um, and like will probably eventually become tidally locked with like the sun. Uh, but that'll be real. That's it's cool. Like orbital mechanics is so cool. Like for example, if you look at in the asteroid belt, there's like gaps. There's these bands of gaps where like the tidal forces from the relative pull of Jupiter versus the sun like meet at whole numbers, and it's like rocks can't exist there because there's too much energy ripping them apart. And so there's these like perfect bands of empty space in the asteroid belt. Space is cool, you guys. Space is so much fun. Science is fun. Okay. Oxygen isotope records of planktonic foraminifera. I never took Latin. Apparently indicating the last Eocene and Og- Oligocene Oligocene, tropical sea surface temperatures were up to 8 degrees Celsius lower than 2 days. Yet, this part of geological history was supposedly characterized by a generally warm climate. Okay. Um, let's look at that Schrag 1999 paper. Um, he says Schrag's solution was to invoke alteration by diagenic recrystallization, which involves incorporation of relatively oxygen 18 rich bottom water into the shells. Um, as electron microscopy has shown, calcite can be added inside the shell or even replace its original structure, both effects being undetectable by standard microscopy. Okay, so let's look at that Scragg 1999 paper. Um, doo, doo. Um, effects of diagenesis on the isotropic record of late Paleogene tropical sea surface temperatures. Cool. All right, copy that. Let me share um just Chrome. Okay, we'll start there. Share. Okay. Okay, and paste. Cool. All right, let's just read this abstract. Oxygen isotope records of planktonic foraminifera indicate that the late Eocene and dude, he literally, guys, he literally, this is word for word. He literally like plagiarized this sentence. It looks like he just copy and pasted it. Uh, oof. Okay, cheese. Okay. Um, so what he's saying is that there was data, Oxygen 18 data said that that this temperature was 8 degrees Celsius lower than present, um, at a time when other measurements of sea surface temperature were higher, and so that doesn't make sense. Um, Specifically because like high latitude sea surface temperatures, so like towards the poles, were higher than present. So like there's no world where he was comparing data, like paleoclimate data from the same time at two different locations, right? Towards the equator and towards the poles. There's no world where the equator is colder than the pole, right? That's not how spheres work. And so what's going on with that? Um, okay, using numerical model, which describes oxygen isotope exchange during burial and recrystallization of deep sea carbonate, the effects of diagenesis on bulk carbonate oxygen 18 records from the Cenozoic are quantified for 4 tropical sites. Most of the observed variations in measured oxygen 18 values at all sites can be accounted for by diagetic effects. Okay, cool. So that's what he's saying is that like um this tropical data wasn't jiving with the high latitude data. And it turns out there's a process that we can like model, right? That we can understand. Um, and to replace replace some of the oxygen in our buried seashells, right? So replace oxygen, cool. Um, and uh, our model, right, was able to account for the difference in oxygen 18 to get those two data points to jive. So yeah, cool. Okay, so cool. So that doesn't sound like a problem to me. Am I oh, I'm so sorry. You guys weren't looking at the paper I was reading. Um my bad. Let me change what you're looking at. Um, share screen. I would like to do. Oh, I meant to do this. Okay, sorry. This one. So this is the paper I was. This is what we were just looking at. There we go. This is what we're looking at. That's the abstract. And so all this abstract says is that like, yeah, we had two data points that didn't jive. And turns out there's a process that can affect this data point, and we investigated that process. Now we understand it, and that process accounts for this difference in temperature between this point and this point. So we can correct our data. We can make our data better. So I get really upset when creationists are like, What? They learned new information and updated things? It's like they corrected themselves? Like, yeah, my guy. Why is that bad? I don't I don't understand. Okay. So, we're going to go back to our PDF. All right. We were up here in the preservation issues. Um Here we go. Do 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 do. Um okay, so here's another study analyzing the same type of thing, planktonic foraminifera, and their samples were examined with an electron microscope to ensure that they were exceptionally well preserved. So presumably that like carb or oxygen replacement process wasn't happening. The inferred sea surface temperatures were 28 to 32 degrees Celsius, considerably higher than the figures given in most comparable previous studies. Um, this further implies that recrystallization could have introduced major errors in previous studies, especially for planktonic foraminifera. Fossils of benthic organisms such as brachiopods, bivalve mollusks, and benthic foraminifera are less prone to recrystallization because bottom water is considerably consistently cold. Okay. Yeah. Okay. So you've got to be careful what samples you use. Okay. And potentially adjust them where needed be. Adjust for temperature changes as need be. Cool. Okay. Perez, Huerta, Coronado, and blah, 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 systematically review the role of biomineralization in our understanding of the fossil record. Cool. They first note that biominerals consist of a mineral phase and a multi component organic matrix in varying proportions, although fossils often retain little or none of the organic phase. True. Okay, yeah, fossils aren't organic. They've been replaced by minerals. Excellent. Okay, I know enough geology to know that. Then they systematically describe one, the basic characteristics of biominerals. Although there is an immense variety of these in existence, they share a number of key recognizable characteristics vis a vis hierarchical organization. Cool. Okay. How to recover primary biominerals and fossils. Preservation of the original mineralogy depends mainly on whether it has crossed its solubility threshold. So this is saying that like most fossils don't have any of the organic bits left, but some have a few organic bits left. And this is how to figure out if you can get those organic bits out. Excellent. Um, Thus, for calcium carbonate fossils, the original mineral form, um, argonite or calcite, is important because argonite is more soluble than low magnesium calcite. The factors involved in diagenic alteration of fossils and the techniques available. Okay, sorry, he just summarized a review paper, and I don't fully know why. Um, that's okay. Let's keep reading. Uh, do 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 do. Okay, modern technology are used to detect and evaluate the effects of diagenic alteration, which I think is the like, can after the thing forms, how do we swap out atoms? Right? How do you get the organic bits out and replace it with like, rock? These have recently been supplemented by atomic force microscopy. That sounds like something out of a Silver Age comic. But supplemented and field emission secondary electron microscopy. Cool. Which can show biomineral structures down to nanoscale. Cool. Um, so detailed characterization of the shell mineralogy was key to this discovery. However, an important corollary is that earlier studies of environmental indicators in fossils undertaken before these highly sophisticated techniques became available. The exact state of preservation of the follows was unknown, implying the reliability of the results is uncertain. But yeah, but my dude, like that all that's saying is like we have better methods now than we did in the 60s. And I think the conclusion he's trying to draw is like, therefore, the data from the 60s may be sus, right? And like, I don't disagree with that statement on its own. Um, Slam Martin and Anti Yek channel. Oh my goodness, have I got friends for you? Check out Dapper Dinosaur, Gutsick Gibbon, Creationists. Um, we're all friends. We do some anti-Yek stuff. It's very fun here. Um, I love the science team. Okay. But I'm super happy you were here and welcome. Okay. Um, uh, I'm reading chat. Sorry. If science changes, that means it was wrong before, which means it's wrong now, which means it's never been right. Yeah, excellent. Thank you for the sarcasm notation, guys. I need it. I need one of those in real life. I need that to just exist over people's heads, but at least on the internet, please. Um, cool. Okay, Star Song, I can't tell if you're being like facetious because you named somebody Professor Moriarty, which I only know as a Sherlock Holmes villain. But if they have like videos and stuff uh on atomic force microscopy, that's super cool. And I hope that's real, but I can't tell. So um okay, yeah, so the point he's making here is that like we're better now than we were before at knowing whether our like the oxygen 18 ratios we're measuring are indicative of the time the shell formed, right? We're better at that now than we used to be. And so like and so then the author here is implying like therefore we can't trust any of that old work, right? I'm like, no, 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 my guy, you're missing the point, right? Is that okay, so we got better at it, and then we reevaluated those data sets and made our data sets better, right? But and if the result of that had been, right, that original stuff by like Shackleton in the 60s and 70s was wrong, that's what the literature would say now, right? But no, like it's a difference between accuracy and precision, right? Like Shackleton's work was ac- was less precise than it is now, but that doesn't mean it wasn't accurate. And that's what we found, right? Right? Like we found um think of this as like shooting an arrow at a bullseye, right? Um uh Maybe Shackleton their data got them on the target, like on the very edge, right? And now we're getting closer and closer to the bullseye, right? But they didn't miss the target, right? Like it's just more precise now. It's better now. Like and again, with better data, those old assumptions are reevaluated. That's what science does, and found that his general results, right, were still good, right? We were on the right target the whole time. Now that we have better data, we can get closer and closer to that bullseye. I hope that makes sense. Okay. Uh, and this is also like kind of frustrating because it seems to me that the author here is trying to imply that if a data set has any issues or any complications, if you have to take anything into account when you're using it, then it's bad and you have to fully throw it out, which is silly. That's not how things work at all. That's like saying because the oven in my house can't get to 1,000 degrees Fahrenheit, right? Or can't be used as a pottery kiln, then therefore it's bad at making cookies, right? Therefore it's bad for baking. Like no. Like just because tools have limitations doesn't mean that they have to be fully thrown out, right? Like I'm sorry we don't have a sonic screwdriver, my guy, that can do anything, but like meh. All right. Okay. Vital effects. How many 12 people watching. You guys are lovely. And I'm going to keep going. I know the last few of these videos were only an hour, but like I've got a good wind going. The baby's down. We watched Bluey. And she's asleep. Um, my goodness. One of my favorite things Baby Girl does right now is if you hum the Bluey theme song, which I won't do because it is a bit of a earwig. Um, she will just start dancing, and it's pretty great. Okay. All right, let's go through the vital effects. Marine organisms which produce fossils of interest for temperature reconstructions generally live at the same temperature of the ambient water. Yep. However, biomineralization, the formation of their hard parts, is biologically controlled and therefore does not necessarily occur in isotopic equilibrium with seawater. Hence, oxygen 18 values and biominerals may not be truly representative of ambient conditions. Okay, like that's fair. So, like, what this is saying is that, like, sure, the organism is in like temperature equilibrium with the water, but uh that doesn't mean but if what that organism does is like what if that organism is preferentially pulling oxygen 18, right? um then the oxygen 18 in the shell is not indicative of the oxygen 18 in the water. That's a great question, right? That seems like a great question to ask as is this a good method? I feel like somebody asked this, right? I feel like this is not an open question. Paleoclimate stuff is not like my specific field, so I don't know off the top of my head, but let's keep reading. But like if we were developing this method from scratch right this second, that would be a great question. The issue for me here is only like, has anybody already answered that? Okay. Examples of identifiable vital effects in Plectonic foraminifera were reported in this paper in 1998 in laboratory culture experiments on the symbiotic species this thing. Sorry, I'm not going to try to pronounce the Latin. Anytime I try to pronounce strange words like that, my like hick accent just gets thicker and thicker and thicker until words turn into molasses in my mouth, and I can't do anything about it. Cool. The temperature range was 15 to 25 degrees Celsius. That critter lives in the photic zone, hosts photosynthetic alga symbiotes, which are thought to modify the carbonate ion. Okay, which is 1 carbon, 3 oxygen. Concentration enhance, hence pH locally, depending on the light level. Well, that's cool. This in turn modifies the oxygen 18 difference between the shell calcite and the seawater, such that in high light and with normal ambient carbonate levels, oxygen 18 in the critter is depleted on average by 0.33 parts per million. Right? Parts per mil? Yeah. Relative to its low light value. That might be parts per. No, I think that's mils. Okay. This change corresponds to temperatures overestimated by 1.5 degrees Celsius, possibly explaining a widely observed discrepancy of the magnitude between temperatures based on standard temperature to oxygen 18 calibrations and temperatures measured in situ for planktonic and shallow water benthic foraminifera. Cool. That's actually really cool. Sorry, he's describing something that's like a cool process in my brain that is a cool process in my brain. And the cool process is, yeah, okay, so there's this critter who like because it's doing photosynthesis, which is cool, or things on it are doing photosynthesis. I'm not fully understanding the process, but it's like affecting its environment very locally. And so, therefore, because of that very local change in environmental like temperature, the oxygen 18 ratio in that critter's shell is different than the oxygen 18 ratio in the like ambient seawater. And so, if you use that critter's shell, as your thermometer, right? Then you can be off by up to 1.5 degrees Celsius, which, if we're talking about global averages, is a big deal, right? That's a big difference. Um, so that's really cool that they figured out that process, and that would change how you calibrate things. So all of this, by the way, all of these things he's citing as like problems, to me reads as a whole bunch of people doing really good science to continuously improve our methodology, right? Again, using the analogy of I fully broke this fidget I made myself while I was fidgeting with it. I managed to tear the yarn in half, which maybe tells you how much I need a fidget. Um, okay. Can I tie it together? I don't think that's gonna work because I knitted it originally. Eh. Okay. Um, um, Using our analogy of the bullseye, right? To me, all this author here is doing is summarizing ways in which people are helping the paleoclimate community, right? Like narrow in on that bullseye. But he's saying because this work is being done to narrow in on bullseye, therefore we must be on the wrong target, right? And I just don't buy that. Okay. Um There's seasonal effects on carbon isotopes. That's cool. They found little interspecific variation. Um, cool. Okay, so he just keeps summarizing papers, and it's going to be stuff that's like not in my field, and so I'm not going to understand the details. Um, so I'm trying to look for like a summary paragraph. Okay. Let's look at this paragraph. It is perhaps worth noting here that while biomineralization, specifically the formation of calcite shells by marine invertebrates, is biologically controlled, it is also affected by seawater chemistry. Thus, for example, calcitic bivalve mollusks grown in artificially high magnesium seawater were found to secrete argonite on their interior shell surfaces. That's not a summary paragraph at all. Cool. Um, okay. We'll kind of skip through this because I think this is just going to be keep being pointing out places where people have improved methodology and claiming that that's a problem. Um, okay. Um, so this next section is seawater oxygen 18 levels. Um, Look at it. Sorry, this is paleoclimate temperature data. It's so pretty. Okay. Um, I think I think yeah, let's read seawater oxygen 18 levels. Let's read it. Okay. The oxygen 18 level in fossil shell material depends on both its formation temperature and the oxygen 18 value of the seawater. We assume either that the global ice volume is negligible or that its effect on seawater oxygen 18 values have already been accounted for. Okay, cool. There is naturally some spatial variation in the oxygen 18 level in the oceans. Cool. Thus, according to Grossman 2012, the bulk of modern seawater, represented by deep water masses, has a relatively narrow oxygen 18 range from about negative zero point zero 0.06 per mil to plus zero point 0.1. I think that percent there means like per thousand, which is why I keep stumbling over it. I know he defined it up above. Well, okay, he defined it up above. Let me double check. I was like, but I don't want to be bothered to look at it. Okay, yeah, parts per thousand. Um, parts per thousand per parts per thousand. Okay, I will say parts per thousand. I think that means per milliliter. Um, that makes sense per milliliter. Okay, we'll say parts per thousand. Um, excellent. Okay, narrow range. Open ocean surface waters are more variable, ranging from about negative zero point 0.5 parts per thousand in the Southern Ocean to plus 1.4 parts per thousand in the dry subtropical zone in the North Atlantic. Oxygen 18 variability in the surface waters of enclosed seas, such as the Arctic Ocean, the Mediterranean Sea, and the Red Sea, is even larger, from -2 to +2 parts per thousand, owing to the varying balance of evaporation and precipitation. There is an acknowledged correction for the effects of latitudinal variation in the precipitation evaporation balance in the southern hemisphere. Cool. Close to continents, mixing with fresh water can lower the oxygen 18. Um, In some circumstances, this correlation means that oxygen 18 becomes primarily a proxy for water density rather than temperature. Cool. Other factors. But like water density outside of the Arctic is primarily a function of temperature. The other thing it would depend on is salinity. And that's like only the okay. Um okay. So I don't see why that's a problem, right? I don't see why that's like again, like that doesn't mean we're off the target, right? That doesn't mean um that you know that maybe is a reason for us to prevent us from getting a bullseye, but that's not a reason for us to be off the target. Other factors include water depth, global ice volume, which affects salinity because freezing seawater excludes salt, and precipitation, which reduces seawater oxygen 18 locally. Cool. Spatial variability of oxygen 18 in Holocene oceans is thus reasonably well understood. However, temporal variability has been controversial and harder to pin down. Practically all investigators, notwithstanding scatter and variations in both directions, have found that fossil oxygen 18 levels increase progressively upward through the geologic record. Some have treated this as a diagenetic artifact, while others have deduced a rising level of oxygen 18 in the oceans, and yet others have inferred long term cooling. Okay, these folks argue that the oceanic oxygen 18 levels have risen progressively through geological time, citing the across the board consistency of the secular trend in oxygen 18 measurements, including those where sample integrity was carefully checked. The corresponding secular trend confirmed independently by different groups in other isotopic and element ratios. These include carbon, sulfur, calcium, radiogenic, and stable strontium isotope ratios, etc. It is inconceivable to argue that the atoms of oxygen, the dominant structural unit of calcite crystals, must have been massively exchanged during diagenesis, while at the same time none of the other major trace elements or isotopes were affected. Um, okay. What's this? What's this paper? Vesner and Prokop? Weisner and Prokop? Okay. Hmm. Do, 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 do. Temperature and oxygen isotope composition of Phanerozoic oceans, Earth Science Reviews. Okay, let's look at that paper. Um, yeah. What paper am I reading? I'm reading a paper on the heat problem. It's a young Earth creationism thing. From the Answers Research Journal. Um, yeah. So we're talking about oxygen 18 ratios is what we're doing. Okay, so we're gonna share a different screen so we can go dig up what it is he's talking about at this point. Share screen. I would like to share this Chrome window, please. Okay, it's gonna get real inception-y for a second. But I'm gonna go back. Okay, there we go. Cool. Let's take a look at this. Temperature and oxygen isotope composition of Phanerozoic oceans. The temperature of ancient oceans is an important constraint for understanding the climate history of our planet. The classical oxygen isotope paleothermometry on fossil shells, while very proficient when applied to the younger portion of the geologic record, is believed to yield only unreliable results in the Phanerozoic deep time, either because the empirically well documented secular trend to more negative. What in the world? Sorry, this sounds like a young earth creationist paper, but because it's using that phrase secular trend. Um, what did I find? Along again, they're putting deep time in parentheses. This is captures. What is this? Okay. What is the secular trend? Um, okay, hold on. I gotta be a little cited by 296. Okay, that's pretty well cited. Let's look at this. Okay. Earth Science Reviews. Astronomically dated record of Earth's climate and its predictability over the last 66 million years. Okay. And then let's look for where this paper cites. My gosh, I'm having to do a little like science journalism, what's the word? Like investigation. It's like an autopsy. Here we go. Because I want to look for where that paper in Science cites this paper. And I also want to look at um, the art, like what is the journal we were just looking at, right? Thank you. Here we go. And one more. Okay. What is Earth Science Reviews? What is that? What is this journal? That sounds like it should be a real journal, right? Okay. Okay. Earth Science Reviews is a monthly peer-reviewed. Okay. Well, that's not helpful. What is an impact factor of a journal? Okay. It's the official website. No. Okay. All right. keep with me, folks. Temperature. So this is J V. Okay, VEIZER. We're gonna look here and look for. Okay, VEIZER. Look for where that's cited. Um, and it's in. Oh my gosh, show me all the references, please. Show me. Where is it? There it is. Okay, so reference 8. Mhm, mhm. Okay. Okay. Compilations of these deep sea isotope records provide compelling chronicle of the past, and transient events in the climate systems from the late Cretaceous to today. However, okay, so that's just the he cites it as this like list. Um, is there anywhere else? No, it doesn't look like it. Okay. Who is this person? Who is this author? Okay. In Ottawa. I'm popping over to look at popping over to look at chat. Sorry for Inception. Okay, hello. Okay. Ah, sorry, that like the wording here is bothering me in this paper. Who is this person? Oh, I can't look you up. Great. Okay. Ah, I found myself because this is like this looks like it might be a real journal, and this is like really cited. Um, but I'm thrown by two of the phrasings here. Putting deep time in parentheses, that feels like a YEC like dog whistle, right? And then keeping referring to a secular trend, right? Um, that also feels like a YEC thing. Um, long overdue tool for interpretation of deep time geologic history. Like in putting that in quotes is bothering me so much. Okay. Um, maybe I'm just gonna go down and look at their conclusions. Okay. Do, 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 do. Oh, actually, yeah, summary. Okay. A collection of 58,000 ish oxygen 18 measurements in low magnesium calcitic shells of fossils, foraminifera, brachiopods, belemnites, and bivalves documents a consistent trend of about -6 parts per thousand throughout the Phanerozoic. This internal consistency provides a template for proposing new baseline values for evaluating oxygen isotopic composition of ancient seawater that in turn enable calculation of ambient habitat temperature for fossil taxa. The preferred paleotemperature ranges are 14 to 32 degrees Celsius with a mode of 24, okay, et cetera, so forth. Um, the history of chemical and isotopic research convincingly demonstrates that the original ideas of fixed ocean water compositions were invariably superseded by recognition that the system is dynamic, variable, and evolving, a realization strenuously resisted for oxygen isotopes. It is only with the acceptance of such paradigm shift that modern, like actualistic outcomes for ambient habitat temperatures of ancient fossils emerge. Um, thus providing us with a new, long overdue tool for interpretation of this deep time geologic history. I don't like that that's in parentheses. Um, but what that summary says, right? I will summarize the summary. What that summary says is that uh, in this certain like it is basically like, okay, we found another issue with this tool. Um, and I unfortunately I feel like I'm out of my depth enough that I don't fully get what his like and therefore conclusion is. So let's stick with I'm gonna stick with this little rabbit trail we're down for a little while. Because I want to see um let's look at some of the other papers that like cite that guy and see what they have to say. Okay, so we're gonna go back to here. I'm going to no, I'm gonna go back to here because I'm sharing the Inception window. Okay. One of my favorite things about Google Scholar is that we can do this cited by and click that. So let's maybe look at okay. Future climate foreseen potentially without president. Yeah, precedent. That feels right. Let's look at okay, let's look at this. Ocean temperatures through the Phanerozoic reassessed from Scientific Reports 2022, Nature. Um, that looks good. Okay. Oxygen isotope compositions of carbonate and phosphatic fossils hold the key to understanding Earth system evolution during the last 500 million years. Unfortunately, the validity and interpretation of this record remain unsettled. Okay, thank you for saying that. All right, cool, 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 cool. So, how good is our tool? We're not super sure. Excellent. Unfortunately, okay, our comprehensive compilation of Phanerozoic oxygen 18 data for carbonate and phosphate fossils and microfossils, totaling 22,000 and 4,615 analyses respectively, show rapid shifts best explained by temperature change. In calculating paleo temperatures, we apply a consistent hydrosphere oxygen 18, correct seawater oxygen 18 for ice volume and paleo latitude, and correct belemnite oxygen 18 values for oxygen 18 enrichment. Similar paleo temperature trends for carbonates and phosphates can confirm retention of original isotopic signatures. Average low latitude paleo temperatures for shallow environments decline from 42 plus or minus 3.1 degrees Celsius in the earlier to Medio Ordovician to 35.6 plus or minus 2.4 degrees Celsius for the late Ordovician through the Denovian, then fluctuate around 25.1 plus or minus 3.5 degrees Celsius from the Mississippian to today. Great. The early Triassic and Middle Cretaceous stand out as hothouse intervals. Correlations between atmospheric CO2 forcing and paleo temperature support CO2's role as a climate driver for the Paleozoic. Okay. All right. So what that tells me is um what does that tell me? What does that abstract say? That abstract says um uh okay. So like this is how abstracts work, right? Um this is the thing we're talking about, and then the next sentence is usually like this is the problem we're trying to solve, and then they kind of outline what they did and what their results are. Um so like what this is saying is that hey, we're talking about oxygen 18 ratios in these types of fossils, understanding to build a paleoclimate thing temperature data record. Um uh Unfortunately, there's been some like debate over how good this record is. So we compiled a big record and this is what we get. That's kind of what this says. So uh okay. So to bring that all the way back to that was a bit that was a bit of a rabbit hole, team. Okay. So let me stop Inception and let's chat about what we figured out. What we figured out is that in the Answers Research Journal thingamajig paper we were reading, he was trying to bring up issues with like challenges to dating ocean temperatures in the Phanerozoic. Cool. Like I said, like paleoclimate is not my specific field, so I'm kind of like learning along with you guys here, trying to just like read an article like I would read an article when I'm learning about anything new. Journal club. That's why this is journal club. Okay. Um, so he cites a few papers that are talking about like I got hung up on that one paper because they were using like YEC kind of dog whistles, right? And I was just like, wait a minute, was getting a little bit of whiplash. So I don't know what's going on with that. I don't know who those two guys are or why they kept putting deep time in quotations. That seems sus to me. Still, that seems real sus. But we found that paper in Nature. Like if I can find a Nature or a Science paper, right? Those are usually like those are so hard to get published, team. Those are so hard to get into those journals. Um uh and they're very good, right? Um and so like that's a great place to look for like an overview because Science and Nature are also like interdisciplinary journals. Like you can get planetary science and biology in the same journal, and that like never happens. So they're not super specific, but they're great for like big picture kind of stuff. Um, uh, and then what happened? Okay. So, and basically, there has been quite a bit of debate about how good our record is in the Phanerozoic. And that seems like it's an active field of research. And again, not to just beat this dead horse, but it's none of them were saying, except maybe that one paper with the quotes and deep with the deep time in quotes. But none of the other things we were looking at were saying we've missed the target entirely, right? It's the how precise can our measurements really be? That's that's kind of the gist. That's what we're talking about. How precise can our measurements really be? Um, not again, not did we hit the target or not? Okay. Okay. Also, I would love to know how in a year you could make a new shell during the flood, right? During the catastrophic flood with catastrophic plate tectonics. So you have the Earth's crust moving at race car speeds, right? How in the world are little mollusks making their shells, right? And then they make their shell and then they die and then they're buried. And then that like replacement process happens to like swap out oxygen 18. Like how is all of that happening in a single year? Please describe that process to me. Right? If you're saying that like that's the target we should be looking at, please explain that process. Okay. All right, we've been going about an hour and a half. I'm having a lot of fun though. It is 9 my time. Let's see if we can't get a little farther in the original article. So let's go back. I'm super thankful. There's like 10 people hanging out according to my StreamYard calculations. Thank you guys so much for hanging out. I miss doing live streams. So, all right, let's go back to sharing. Here we go. Okay, we're gonna get out of that oxygen 18 stuff, and until we can find something that this author has to say. Um, I'm so excited of problematic heat flow data. I'm so excited to read that bit. We're not quite there yet. Okay. Doo-doo-doo-doo. Interpretation of the data in terms of flood geography. I think maybe let's skip to that. Um, okay. Okay. So let's look at this section. Appraisable, my goodness. Appraisal of oxygen isotope data. For flood models, such as catastrophic plate tectonics, the Cenozoic represents the post flood period, characterized in its late stages by the growth of ice sheets in an ice age. That's right, folks. For the creationists, there's only ever been one ice age, and it was immediately post flood. As noted earlier, other flood models, the correspondence of ocean floor development with flood chronology will vary depending on where the flood post flood boundary is placed in the geological record. The question is considered further in section 3. Cenozoic oxygen isotope data are reviewed by Zakos et al. 2001 based on oxygen 18 measurements in the Caloris fossil remains of two types of common long lived benthic foraminifera. They treat the oxygen 18 measure as a proxy for ocean floor temperature up to the late Eocene, when the Antarctic ice sheet began to form around 35 million years ago. I refuse to say this because I do not like that terminology. From the early Oligocene, Oleaginous. Jeez, I'm sorry, team. I'm struggling with words. They treat oxygen 18 as a qualitative indicator of ice volume. Great. Although the trend is not monotonic, the overall change in oxygen 18 is plus 5.4 parts per thousand over the whole Cenozoic, which they resolve into 3.1%, 3.1 parts per thousand to represent deep sea cooling. Cool. Um, plus 1.2 parts per thousand for the growth of the Antarctic ice sheet, and plus 1.1% for the subsequent growth of northern hemisphere ice sheets. Cool. Um, okay, I think this is important. The highest global ocean floor temperature is in the Cenozoic, inferred from oxygen 18 data, are approximately 12 to 13 degrees Celsius, occurring at the Paleocene Eocene thermal maximum. Yeah, this Paleocene Eocene thermal maximum, this guy right here, it's crazy. There's this, like, what we think happened is that there was this massive reservoir of carbon, like carbon monoxide, um, released that had been like stored in the ocean that was like released into the atmosphere. And so you get CO2 driven climate change in the past. And it's like temperature, the warmest temperatures of all time ever recorded on Earth. Cool. Okay. Doo-doo-doo-doo-doo. Okay, so this author wants to take that temperature limit as like that's an important limit because that's going to set the boundaries for like the math problem of how much heat did the ocean have to lose during the flood with plates moving around at race car speeds though. Um cool. Um um Okay, this is outlining maybe some of the issues of why Paleozoic and the Phanerozoic is maybe tricksy. Okay. If the observed secular trend is interpreted through a single oxygen 18 ocean temperature calibration with present day standard mean ocean water as the 0 parts per thousand reference, it implies considerable cooling. Um, and, Ocean temperatures today lie between about 0 Celsius and a sharply defined maximum of 30 to 32 on the surface. As noted previously, argue that the oxygen 18 trend is due to secular increase in the oxygen 18. I don't know what secular increase means there in the oxygen 18 level in the ocean water since the Cambrian. Um, I wonder if he just likes the paper because they keep using the word secular. Okay, let's let's skip through this because this is really in the weeds and I'm not sure it's super interesting. Interpretation of the data in terms of flood geology. Let's get started on this. Um, all discussions of complicating issues in the secular literature presuppose the normal chronology, well supported by data chronology, within which the assumption of a climate system approximating to steady state is a meaningful concept. Yes. Yes. The climate being an approximately steady state is a good concept when you have geologic timescales. It's not if you just have 1 year of the flood. Inarticulated brachiopods typically live for 1 to 10 years, and articulated brachiopods for 3 to 30 years, while bivalves can live for 50 years or more, and deep water species up to 100 years. These lifespans are short compared with climate change timescales, correct, typically contemplated with normal geology. In that framework, the concept of quasi steady state may be appropriate. Yeah, it totally is. However, within a biblical timescale in which, say, most of the Phanerozoic represents deposits laid down during the flood here, conditions must have changed rapidly. That is true. If the flood was real, that would be true. Thus, in a catastrophic plate tectonics flood scenario, there will probably have been rapid, large scale exposure of hot mantle rock to ocean water, resulting in considerable exchange of oxygen and significant change in oceanic oxygen 18 levels. Cool. Um, Furthermore, the breaking up of the fountains of the great deep in Genesis 7:11, perhaps as a result of the dewatering of rising depressurized magma, could have injected into the oceans a large quantity of water with a different oxygenate value from that of the pre-flood ocean. That ooh, you're gonna have to demonstrate that to me. So he's saying that like great reservoirs of water were brought up from like under the mantle, which is not supported by reality. Um, and so how would that mess with the oxygen 18 values? Well, so here's the thing, right? If what you're saying is that in the flood, oxygen 18 values would have just been all over the place, changing willy-nilly, getting oxygen 18 from all kinds of stuff. What I would expect from that would be that, okay, so therefore what we measure are oxygen 18 values that are all over the place, right? We've got the fountains of the great deep coming up over here and over there. There's magma suddenly hardening and sizzling the ocean there, and their oxygen 18 ratios are very different. And somehow in all of this that's happening, which remember, isn't enough heat to melt the granitic crust of the earth many times over, somehow we've got little mollusks living their best life, making shells. Because like to those oxygenate 18 values to be different, right? Those mollusks have to like be rapidly making their shells. Like, okay, I feel like we could break down how much of the rock would have to be laid down per day if we thought about it. Um, uh, like we usually think about it in terms of like time, right? And I'm not a geologist, so I don't have these numbers in my head. Um, but like, okay, if we think about like the mass of volume, right? The mass of volume, geez, the mass of rock, right? That would have to have been laid down during this like 1 year of the flood. I feel like that's probably like, I feel like you could almost nail it down to the day if you really wanted to, right? So, like, on average, you're laying down this much every day. So, like, this layer is from the first day of the flood, and this one's from the second, and this is from the third, right? Thinking about averages, right? So what you have is that in each of those layers, let's think of that as like different days of the flood. The all of the mollusks in this layer, right, have this oxygen 18 ratio, and then the next day, all of these have this oxygen 18 ratio, and it's consistent in this location and that location, right? Um, which doesn't how does that happen in a catastrophic flood? Like how does that happen? How do you have again, because like we have to have our little mollusk making its shell, living its whole life today, right? In this one day. For all of in these conditions of this day in this place on during the flood for that to work, right? Like that doesn't make any sense. And again, if what it was that there's all these different oxygen 18 ratios all over the place, then you would expect our record of those right, are when we go to measure those oxygen 18 ratios, then our results would be all over the place, right? That we wouldn't be hitting a dartboard, we wouldn't be hitting the target, we would be covering a whole field. And that's not what's happening. So like how, right? How do you get relatively organized data when you could have crazy oxygen 18 values going off all over the time, all over the place? That's what I want to know. How do you get like how does the flood cause the data to be this well organized, right? Like how? Okay. And again, when would recrystallization occur? Because this next sentence here is unless it has suffered recrystallization, the calcite and fossil shells deposited during the flood year, many of which represent animals killed and buried in the flood, must represent ambient conditions immediately before or in the early stages of the flood. Sure. But when would recrystallization occur? That's not going to happen in 2,000 years or 4,000 years. Like, when is that going to have occurred? If oxygen 18 levels change significantly during the flood, the direction and magnitude of change cannot be predicted. This change should be reflected in calcite and post-flood fossil shells. Sure. In the standard catastrophic plate tectonic model, these would be the lowest level Cenozoic fossils, i.e., from the Paleogene. In flood models, which place the flood post-flood boundary higher in the stratigraphic record, these falls would be found correspondingly higher, whatever have you. Inspection of figure 3 suggests no obvious major changes in the oxygen 18 levels either at the KPG interface or above it, except possibly at the those locations, the temperature maximum, Paleoneocene temperature maximum, and I forget what EECO stands for. Ugh. Okay, some who accept CPT as the basic explanatory framework for the flood would now place the flood post-flood boundary somewhere between the KPG boundary and the Pleistocene boundary. Thus, Baumgartner, who developed the coherent physical model for the coherent physical model, is it coherent? Between the KPG bound. Okay, sorry. Model for mechanisms underlining catastrophic plate tectonics, and was co-author on the Austin paper, places the flood post-flood boundary in the Pliocene. Snelling argues that the boundary must lie somewhere above the KPG interface on account of the large amount of geologic work in evidence in rocks above the Cretaceous. Okay, whatever. These are all where do you put the flood boundary? Have fun. Not all flood models view the geologic record in this way. Brand assumes considerable geologic activity both before and after the flood, though he sees the flood as the single most significant event in Earth history. His model does not predict a clear end of flood marker in the geological record. His creation curse catastrophe model. Wow. Yeah, coherence doing a lot of work in that sentence, Vagary, right? Like, well, it's doing a lot of work there. Ah, okay. Treats the different fossil assemblages in the geologic record as representing different. Yeah, I mean, Stelling is a liar and an academic fraud, so we don't really care what he has to say. Okay, sorry, this is like rambling and putting all of these details when the point that was put in here is that like there's no like clear line or jump in those oxygen 18 ratios that would like give you a pre-fed post-fed boundary. Um, so like there's no evidence of a flood in the oxygen 18 ratios is the point that he's burying in these details. Um, and this is just arguing for why CPT is good though. Okay. If the geological record is understood in terms of a recolonization model in which the flood deposits correspondingly largely to the Hadean and Archean rocks, practically all accessible fossil marine shells will have been deposited over the subsequent 4,400 or so years. Oh no. Oh no, that's not possible, my friend. That would be like the number of organisms you need to make those fossils is absurd. That's not possible, my guy. Okay. It's not. Okay. Uh yeah, miles thick of invertebrates. We humans wouldn't exist because we'd be crushed under the weight of the mollusks. Gosh. Oh my gosh. Okay. Um yeah, but while we're all being crushed by the weight of miles deep mollusks all over planet Earth, um, steady state conditions might be a better approximation of reality. Oh my gosh. Um, that the recovery Tyler envisages that the recovery and recolonization of the Earth after the violence of the Mabul would have been punctuated by further catastrophic events, implying that for much of geologic history, one cannot necessarily assume steady state, given the stratigraphically poorly defined end of the flood in this model. Oh my gosh. End of flood seawater temperature predictions for this model cannot be compared with geological data. Okay. Wow. Wow. We'd all have to like Scrooge McDuck. I'm imagining it's all Scrooge McDuck diving into the pool full of gold, but it's just mollusks. It's just so many. Oh my goodness. Oh, okay. A number of creation scientists have taken at face value published paleo temperatures based on oxygen 18 data, apparently without considering the validity of the oxygen 18 temperature calibration used in their sources. Goodness. However, Veridum 1996 outlines the basics of oxygen isotope thermometry and discusses many of its complicating factors. Oh my gosh. Okay. He cites biological factors, diagenic effects, recrystallization, ecological factors, seasonal migration, which must be accounted for in linking inferred temperatures with climate, Pleistocene context, forum habitat changes between glacial and interglacial conditions, the impact of seawater oxygen 18 values on temperature estimates, but only in relation to growth and retreat of Pleistocene ice sheets, etc., so forth. Um, uh, Gosh, okay. Verdeman does not mention the effect of oxygen 18 levels. Verdeman, by the way, is a creation scientist in this, right? The effect on oxygen 18 levels of interactions between hot mantle rocks and seawater. Yeah, why not? Nor does he consider the possibility of a long-term trend in global oceanic oxygen 18 levels. Excuse me. He concludes that in a flood model context, the accuracy of past temperature estimates is unlikely to be better than 3 or 4 degrees Celsius. Um, okay, cool. Um, so this creation scientist thinks that in a flood model context, if there was a flood, therefore our past temperature estimates are bad. Though that's that's what that says. Is that says um uh yeah, the error bars have to be really big because around this paleoclimate data because there totally was a flood, you guys. It's not helpful. Okay. Regardless of the particular flood scenario assumed, hey, look, assumptions. Creation scientists must inevitably interpret the oxygen 18 record in marine fossils differently from normal good scientists. Oh yes, oh my gosh, vaguery, the flood happened and we're here, so there is no heat problem. I what I was on a stream with Erica and Dan, um, and there was like a creation scientist saying that like, hey, in this rock, there is no evidence of extreme temperatures. Therefore, the flood happened and there is no heat problem we have to worry about. Like, no, you're so close to understanding. No, there's no evidence that there were these extreme temperatures. So, therefore, your flood model, which requires extreme temperatures enough to melt the granitic crust of the earth several times over, couldn't have happened. Jeez. Oh my gosh. The flood happened and we're here, so there's no heat problem. Oh my gosh. Basically. Um, okay. Furthermore, creation scientists have not thus far considered the possibility of long-term increases in the ambient oxygen 18 levels. Thus, further investigation is needed to clarify our interpretations of oxygen 18 values in pre-Cenozoic marine fossils and its implications for past ocean temperatures. You guys have got a lot to figure out for oxygen 18 levels. Because again, how, how during a global flood, right, when we're laying down all this rock, supposedly, how is it sorted by oxygen 18 values in the shells, right? How is it this layer has this oxygen 18 level and this layer has this oxygen 18 level and they don't mix? Please explain that to me. Okay. All right. This next section is surface heat flows. I think we'll pause here. This paper is taking me longer than any paper of all time has ever taken me to read. It's possibly because I'm reading it out loud and I keep having to stop to scream in agony. Um, but I think that's where we're going to leave it for tonight. We've got about 2 hours. Amazing. So, what's coming up for me on this channel? Excellent question. I'm so glad you asked. Okay. So, next week on Thursday evening, I'm gonna aim for 7 Central. It might be 8. Look for the notification, and I'll try to like. Evenings are actually a little easier because the kiddo is asleep. Um, we're gonna 7 or 8 Central do. I'm gonna come on and I'm gonna celebrate my defense. My defense is Tuesday. So that's coming up on my channel on Thursday, and then a week from today, that Friday, we're gonna try to do another journal club. I'm gonna try to do those in the afternoon because journal club should be a lunchtime thing. Um, and then on the 23rd, I will be on Dapper's channel for Matt with Maddie. Normally that would be this coming Tuesday, but because it's my defense, we're swapping. Um, so yeah, that's what's coming up. And the goal here is to get back to doing at least these journal clubs like once a week. Sometimes it's live, sometimes it's pre-recorded. It just kind of depends. I'm trying to get back into a more regular rhythm of doing videos. And so I should like graduate in May and then start my postdoc job in June. And so hopefully that will look like a more regular schedule. Um, and I'll have like a normal human job. And we'll see what we can do. And I'm hoping to get back to doing some of my like my Weather 101 stuff. So my other like education stuff, not just the pseudoscience debunking. But hopefully I'll see you guys on Thursday, the 18th for Drunk Defense. Gonna probably change that name, but you guys can hear all about my research. It'll be super fun. Celebrate with the science friends. So you guys have an absolute wonderful rest of your whenever you're watching this. But for me, it's Friday night. I hope you're having a great day, evening, whatever have you, and I'll talk to you guys later. All right, bye, team.